Thank you. And good morning. And I'm Ya-Jing from Institute of Geology and Geophysics in Beijing. So it's really my honor to be here to share some of my recent findings. So my talk is about the zonation in olivine, and I try to use diffusion in the olivine to constrain the time scale to form the Kalatongke deposit. So first I would like to thank Sumit Chakraborty and Ralph Dolman from the Rural University and for their helpful discussion and the workshop on the diffusion, and Martin from the Lebanon University for the analysis, and Steve for the helpful discussion at the beginning, and my colleagues. So let's say first let's say about how to the olivines in the how to form and the process it may went through during in the nickel copper deposit. It's like firstly, we need to crystallize the olivine from the magma. So no matter it's faster, rapid close or slow close, and after that, olivine will experience the mash process. So the olivine have to equilibrium with the chipped liquid here, and probably some overgrowth dissolving is happening here. And after that, if sulfide percolates into those spaces, and the olivine will going to react with the sulfide. So actually, there's lots of evidence to show that those processes happening in nature. And I think the calcium in olivine is quite a good example to show this. Here is the olivine from the magmatic nickel copper deposit, and this is olivine from the volcanic rocks. We can see the calcium is overall low. Actually, this is showing that the calcium is diffusing out of the olivine when it's crystallized. So, and also the same story for chromium and aluminum, and also the iron and nickel exchange between olivine and sulfide has been demonstrated by experiment from James Brand. And also we can see the nature samples, the olivine with sulfide, we can see the larger scatter in the nickel. Because this is showing the reaction between olivine and the sulfide. So the question is, what time scale is those two processes happen? So actually my motivation is to get some of this study to work on this. So I use the olivine from the Kalatongke nickel deposit in northwest China to try to get some intergrain zoning from different elements. So the measurement I use is high resolution microprobe analysis. So this I will get high space resolution, and also I can get those trace elements, which is very useful for defining the primary zoning in olivine. Weibo yesterday has given nice talk on the Kalatongke deposit. So I just want to mention here is the rock type is mainly olivine gabbro I use. So yes, the next, yeah, point. Okay, anyway. And so next important thing I want to show here is that the size of the intrusion. So this is the Eiffel Tower here. So this intrusion definitely is much smaller than the layered intrusion, but compare the Eiffel Tower, we can see here it's not that small. And sorry, I think it's not moving. Yeah, so I selected, actually the idea is select different samples from the intrusion. Some is close to the rim and some close to the center of the intrusion, and to look at what kind of zoning we get. And yeah, so, okay. Let's start from this. Okay, so this is the first type of olivine. That this olivine is included in the silicate minerals. So it's like for this late crystal-like phases. So this actually, I name it as type 1 olivine. So this olivine, we can see some normal zoning of the iron, magnesium, and also nickel. Oh, it's coming back. Okay. Yeah, it's not going to move forward. Okay, yes, this is for the major elements and right. Okay, this is for the actually this shows some of the magnesium enrichment in the olivine when the olive is there some spinel in it. Actually, this shows like iron and magnesium exchange between the olivine and spinel here. So for the analysis diffusion of the diffusion profile later, I will avoid those spinel because there's some exchange between this phase, because I want to focus on the diffusion of the different zones in the olivine and the diffusion between olivine and the outward melts. So we also can see there's some small common zoning here. And this is phosphorus in olivine. We can see here the map, the rim is a little bit phosphorus rich, and the coal is rich, and the rim is kind of depleted. And we also can see the analysis. There are several different levels of phosphorus. This actually shows the multiple stage growth of the olivine. So if we put all of those profiles together, we can see as the ring, there are some phosphorus pole. They have lower phosphorus value, FO value, nickel content, and higher a little bit higher magnesium. So actually, this is geochemical character shows that the ring is crystallized from the evolved melt. Interesting is for the calcium zoning in olivine. So for this olivine, there's no iron and magnesium zoning, but we can see nicely of this calcium zoning at the rim. The calcium at the rim is depleted. So it's very nice calcium zoning here. And actually what's happening here is the reaction between orthoproxine and calcium in the melt and olivine and CPX. And this reaction is very dependent on temperature. So this is calculation of the calcium in olivine and the temperature. So this actually is very important, because if the calcium in olivine is temperature dependent, so we can use this calcium at the rim to define the boundary condition when do the diffusion modeling. So actually this would be very helpful to get the cooling history of the intrusion. And so next is type 2 olivine. Type 2 olivine is in sulfide. So I am not going to show more maps because this type of olivine is kind of similar, but most different one is that this kind at the rim of this kind of olivine, it's enriched in nickel. This is expected because during the interaction, nickel can come from the sulfide. But what I'm not expected is the phosphorus value is also increasing. That's really bothered me a little bit. So I put the olivine and the sulfide together, use Sankara's olivine and put in the gas tube and put it in the oven to see what it is happening in the experiment. And this technique is followed from the James Brown's review work. And so this is what we get. So this is olivine, and also we get this kind of textures. And when we do the SEM, we can see there's some OPX forming during the reaction between olivine and sulfide. Yeah, but fortunately, when we do the modeling for the time, we can see that the elements, especially the nickel and the manganese and calcium, those trace elements will not be affected by the reaction too much. So the main thing from here is that we still can modeling this process to get some time scale. So last part is the modeling of the cooling rate of time scale. I'm not going to too much detail for the modeling. I just to show the strategy. So mainly is use the different elements because they have a different diffusivity, and also use the phosphorus to define the boundary condition for different stages of the olivine. So because different stages of olivine, they have different conditions, so they will have diffusion. And I will just change the cooling rate and the boundary condition to satisfy all the elements that with different diffusivity. By the way, the diffusivity of the elements in olivine is very well constrained for those main elements like so because we have to model multiple price process, so I use the numerical modeling here. I just show the modeling result of the one grain. This is type 1 olivine that's included in the by the interstitial liquid. So the result comes out that the overgrowth temperature is like 1,000 degrees, and the cooling rate is about 2 degrees per year. And we can see there's some not very good match at the boundary because I said the boundary constrained. So if consider the diffusion flux from the melt, so this can be very well fixed, but this will not affect this result too much. And this is another one. This one is the type 2 olivine that we sulfide, so we can see nickel here. As a ring, the nickel is increasing. Actually, this is nickel is decreasing first and increase. So actually, this shows the olivine has experienced first stage is interacted with silicate liquid and then interacted with the sulfide. So what time we get is like overgrowth took place at similarly at 1,000 degrees, and the cooling rate is about 4 degrees per year. And actually, this sample is sulfide percolate happening. It's around the temperature about 940. So it's like just take decades below the rock has been completely solid. So what does this mean for the cooling rate? So I compare the Kalatongke to the other deposit layered intrusions. This is the case from the low oceanic gabritic intrusion. So this is quite a big one. It's like 2 kilometers thick. So they have get the cooling rate like this. So this is Kalatongke deposit here. And also it's much faster than the layered intrusions as shown by Xin's paper. So actually, this shows that the Kalatongke deposit is a very, I would say, very fast cooling system. So I think I will leave here, and I'm still working on this. So this is not the final conclusion, and I'm looking forward to your comments, suggestions, and questions.
Thanks very much. That was really interesting. So in the diffusion profiles, you had one for phosphorus going out into the I presume into, so this phosphorus dissolving in the sulfide.
Yeah.
So does that imply that all these chalcophile or lithophile elements are soluble in sulfide?
No, actually those. Yeah, I think absolutely not this case because they form the orthoproxene in the experiment. I think all those laser sphere elements is going to orthoproxene,
including phosphorus.
Phosphorus? Good point. I have no idea. Probably I can say just stay there. I guess so. Maybe.
Mao is a very interesting work. I'm thinking, modeling, you use the modeling is just the static diffusion rate,
okay.
But in your sulfide percolation, the diffusion between the sulfide and the olivine, it must be convective diffusion model. I think as you can explain all about this. It's just a static diffusion or just a convection. There's convection and the boundary is always freeze a new sulfide liquid. So it may be diffusion very fast.
Yeah, actually for the sulfide, it's because it's some reaction is going on, should be faster in this process. Yeah, I agree. This if this happens, this might be different, but I think because I did the experiment, And they show that there's kind of olivine dissolving and forming the new orthoproxy. But the diffusion profile actually fit well when you use the time scale, because for the experiment we have time, we can calculate the diffusivity. So actually the model fits well if you assume that they just reaction between the sulfide and you use the fixed boundary condition. Yeah.
I think that's the end of the little conversation.
Let's try 10 to 11.